We are going to prove Baire category theorems. So first we need a definition what a category mean. So we have a metric space X and M as a subset of X. So we say that M in X is a nowhere dense or rare if its closure has no interior points. That means that interior of closure of M, which is this, is empty set. So we have another definition, measure. If M is measure in X, that means that it is a union of countable many nowhere dense or rare sets. So we have countable union, which equal to M, and all for all n, Mn is nowhere dense or rare. Is rare. And if it is not major in X, so it is not major. So if it is written as a countable many union, like union of, then at least one of them must be non-rare. So then there exists n0 natural numbers such that M and 0 is not rare, so which is equivalently it is non-empty. So what about the Baire category theorem? It is stating that if a metric space X, which is not empty set of course, otherwise it is very trivial, is complete, then X is non-major in X. So we do it showing or assuming that the counter is true. So assume that X is major in X. That means that X is countable union of rare sets for all n. Mn is rare. So we are going to construct a Cauchy sequence, and since we have complete metric space, it should converge this point, and so we get a contradiction. So hear me out. So first, starting with okay, let me start this from 1. Okay, M1, which is rare, so has no interior point. So its complement, consider its complement, M1 complement, it is now open. And since it is not empty set, because our X is the whole set, so what I mean is so there are points and M1's complement is open, so it should consist an open set in itself. So we have a ball. But before that, choose a point P1 inside this complement. Then take a ball which is centered at this P1 with a radius epsilon 1, such that choose this point such that this epsilon 1, or choose this epsilon 1 such that it is less than 1/2. We can do this always because since it is open and we can choose smaller balls and smaller and smaller, because if you have this set, assume that open, then you have a point inside. If there is a ball, and you can always take a smaller ball inside it, so you can shrink it. Now let me write a picture and then we follow. So consider, since M1 has no interior, I like to write it like a point, union of points. It's union of points, which is M1, and complement is the everywhere. So let's say that P1 is here and ball is here, so epsilon 1. Okay, now what we want is the choosing the second point so that it belongs to this ball P1, centered at P1 and epsilon 1, and with the intersection of M2's complement. For the M2, we can consider the same argument above, because since it is again a rare, its complement is open and you can choose a ball, but we can choose it like it is intersected with this ball, right? So we can choose another smaller ball here. Let's say this is a B1, and choose an epsilon 2 as epsilon 1 over 2, and P1 P2 belongs to B2, which is P2 epsilon 2 inside B1 intersected with M2C. So what we've done is, okay, let's this be M2, and we choose second point so that it included inside here. We can choose it because it is their both complements is open and they are not intersect with this ball, because they are they have no interior points. So choosing this P2 here and choosing the smaller ball here is enough for us to continue. So inductively we are continuing that way, so that at the end what we should expect. So let's say we come to kth index for k. So our construction here follows, and bk is bpk at with a radius epsilon k, right? And we know that if you go one step further for k, the bk plus 1 should be inside of this bk, and which is, and there exists some ball behind, so we can do it a better, we can do and write it a better way. So there exists a pk also, because pk plus 1 is different, you are intersecting with the mk's complement, so there exists some little ball 1 over 2 epsilon k, and which is belongs to pk, of course. Now, so following from the epsilon 1 here and epsilon 2 and epsilon 3, we got the following inequality, which is ak epsilon k is less than 1 over 2k, since it first is less than 1 over 2 and second must be less than 1 over 4, etc. So you see that this should be giving us a cautious sequence. So if you define pk's as a sequence, then it is Cauchy sequence because of above argument. And since X is complete, pk's must converge some P. Let me write it in that way. Some P element of X. So we have a Cauchy sequence, so it converges to a point. So we have a convergent sequence, which is pk's right here. So what we do now, we are going to show that this P doesn't belong X by showing that this P doesn't belong any of this Mn above, so that since it is the union of these Mn's, so it cannot belong to X, and we end up with a contradiction. So how we do it is the following. So let's let any M be given arbitrarily. So you fix this temporarily, and for every n bigger than m, you can say the following things. Because of the above arguments, we have bn's subset of pm epsilon m over 2's. The length between pm's and p is less than, by triangle inequality, dpm pn. It should be shrunk to the 0 because we have Cauchy sequence, plus dpn and p. And this is going to be also shrunk, but because it is convergent sequence, so for every m this goes to 0. Of course it is trivial, but let me here add, because it is not trivial, because you can say that for every epsilon you have fixing big N, and for bigger n's than n, yes, you expect that your point converges to F. It is trivial because our sequence is convergent, but we are fixing arbitrary m temporarily, so it doesn't go infinite, or it doesn't bigger than any fixed value, so we cannot use trivially convergence argument here. That's why we are separating this by triangular inequality. Anyway, then which is also equivalent to, since it is in this ball, we can say that epsilon m over 2 or less than, plus, since it is convergent now for a fixed value, it can vanish. So it goes to epsilon m over 2 for now. But hear me out. Since the p's in the bm's, and which is equivalent to inside mc's complement, mm's complement, so you see that p is not element of mm's. So that means, since the m was arbitrary at the beginning, so for every m natural numbers, so p can't be element of, but which is equivalent to x, but at here we show that p is element of x, so we got God, contradiction. So thank you.